Good morning and welcome to yet another extravaganza. Today, what we intend to look at is Ohm's Law, and I'm going to look at the prescribed practical on page 456. And what I intend to do is to just say a few words about Ohm's Law and what resistance is. Then I'm going to explain how to draw the circuit. Then I'm going to give you a set of results. Then I'm going to show you what graph I want you to draw from these results. Then I'll show you what's important in the graph. And then on page 456, 457, your task will be to copy out the prescribed practical. The reason is you're copying out, you've seen it once, you've done it once, you're going to draw the graph, you're going to find the gradient, and then you're going to look at the conclusion from the graph, and then you're going to upload that for me for marking. So that's what you have to do, and that's what I have planned. So we'll continue. So we're going to look at Ohm's Law here. So I suppose we better put in page 456, 457, and I better change the thickness of the pen. Right, so let's go down and talk about Ohm's Law first. Ohm's Law. Now Ohm's Law is named after the scientist Ohm. His name was Georg, I think, but we would know it as George. So he's a scientist, and he gave his name to the Ohm's Law because he investigated it. And when you really think about electricity and Ohm's Law, we only use electricity really for two things: heat and light. And heat, light and movement. Heat and light's very similar. If it's very hot, it's white hot and gives you out white light. If it's not very hot, it gives you out red light, like the bars in electric fire. And it also gives you movement, but movement is to do with the magnetic fields associated with current electricity, and we are not doing that at this moment in time. So we're going to look at Ohm's Law and see what Ohm's Law states and the constraints of Ohm's Law, and then we'll see why this thing called resistance exists. So Ohm's Law states that the voltage is proportional to the current at a constant temperature, and it's the constant temperature that really is it's very important, the constant temperature, but it's a sort of its own nemesis, because once you heat a wire up, once you put more current in, once you put more voltage across it, well, then you heat it up, so therefore the temperature doesn't remain constant. So Ohm's Law is a very difficult thing to prove, because you have to keep the temperature of the conductor resistor constant, and that is difficult. So let's follow the blue spot yet again. The voltage is proportional to the current at a constant temperature, and if it's proportional, V is proportional to I, then what you can say is that V is equal to a constant times I, and this constant is known as the resistance. Fair enough. Now the voltage is measured in volts, and voltage is one of these hard concepts to get through your head, but the best way to look at it is that it is like a force. Notice I didn't say it was a force. It is like a force in that it gives the electrons energy to move. Fair enough, but it's not a force. And then the current is measured in amperes. And the resistance, this constant here, I'll change the pen, I'll put a bubble around it. This constant is the resistance measured in ohms. Fair enough. So that's what we are trying to look at. So what is this resistance? So well, resistance is the opposition to current flow. So it's the opposition to the movement of electrons. That's what it is. It's trying to stop the electrons moving, right? So we'll write that down. It's trying to stop the E's moving. Fair enough? And why is this? Well, The coldest temperature that we know of is a thing called 0 Kelvin, minus 273 degrees Celsius, or centigrade. And this is the coldest temperature because temperature really measures the movement of atoms. And if you keep cooling atoms and cooling them, their movement will eventually stop. And it stops at this temperature called 0 Kelvin. So anything above minus 273, which is rather chilly, I suppose. Outer space is about 2 Kelvin. Anything above minus 273, the atoms move. And the fancy name for this is thermal agitation. And this thermal agitation now the way the atoms are arranged is called the crystal lattice. So it's a thermal agitation of the crystal lattice that tries to stop the electrons moving. And the analogy I have for that is, there's 3 dogs. They're not very convincing, like, but take my word for it, they're 3 dogs, right? And there are no dogs harmed in this demonstration. And if you're an electron jumping, I'll change the colour of the pen. If you're an electron jumping from, see how it's jumping from atom to atom there? Well, if you're a flea jumping from dog to dog, and these dogs are moving, see how I went into the 3rd colour there? I suppose you're impressed. If they are moving, the flea would find it more difficult to jump. So the analogy is the electron would find it more difficult to move because it'd be impeded. So therefore, if you increase the temperature, less electrons move and the resistance increases. Fair enough? So we'll try to put this into ordinary science. If that's a positive ion, in other words, an atom that has lost an electron, and that's a positive ion, the electrons jump from positive ion to positive ion, and that is current. If these positive ions oscillate because of the thermal energy that they're getting, the electrons find it harder to move. And if the electrons find it harder to move, you resist their movement, and that's what resistance is. Fair enough? So my analogy up here of the dogs, with the flea jumping from dog to dog, is the flea is the electron, the dog is the positive ion, and I'm not going to heat up any dogs for this. So that's what resistance is. It's the opposition to current flow, the opposition to moving electrons, due to the thermal agitation of the crystal lattice, which tries to impede or stop the electrons from moving. And that's what resistance is. So now we're going to have a look at the diagram. Make sure I'm in the black pen here. I'm going to look at the diagram. So you can come over here, please. Come over here. Lovely. I'm going to look at the diagram that we need to set up to investigate, is the resistance proportional, or is the voltage proportional to the current? So there's my battery, there's my anode, and there's my cathode. Remember, the long one's the anode, positive, negative. And again, notice that I'm drawing this with a ruler. See, when I'm marking stuff and people aren't drawing stuff with rulers, they're not doing themselves any favours, I can tell you. Your work's through other. So I'm trying just to make this as tidy as possible, and doing it in the virtual world, which I am doing. Sometimes it doesn't do it like it didn't do it there. So we'll try it again. There's it done again, and there's a bit there needs to be done. Over to there, and that needs to go up there, and I need to put that in there. Now you should be able to draw this. You know, people say to me how to study. Practice drawing this will be enough for you. And there I have to put a variable resistor in there. Exciting stuff, this. And then I'm going to show us a variable resistor because I put that sort of arrow or bar through it. You see that? Oh, it didn't come through. So I'll try it again. There you are, you see that? That's your variable resistor. Here's our fixed resistor. See the way I have it drawn in now, just keep following me. There's the fixed resistor. So I'm nearly finished. I just to put the 2 devices in to measure current, and remember Agatha the ammeter. Agatha always makes an ass of herself. Second, not going to be on it. well, ammeter, small resistance and in series. Not there, it's just not. The pen's misbehaving today again. You might get the heave-ho. I'm going to put in Vince the voltmeter. Remember Vince with the bandy legs? Severe case of rickets. There's Vince. Fair enough. And the Vince, the voltmeter, is parallel and has a high resistance. So let's just follow the blue dot around the screen now, and I'll talk my way around it. There's my anode, the long leg of the cell is the anode. There's the cathode. So I'm going to go around, follow the blue spot, and then I come to this. There's a switch. And the purpose of the switch is you can turn the current on, turn the current off. And the reason you turn it on and off is that you want to keep the constant temperature. Do you see it there? Look, constant temperature. Follow it up. I'm up, pointing there. Do you see a constant temperature? So that's why that switch is there. It's also connected to the anode because that's just the way it is. It's supposed to be a safety thing, but in some diagrams you'll see it on the other side. So now we'll come down to the ammeter. It's an ammeter, A-M-M-E-T-E-R. It's not an amp meter, you lose marks for that. It's an ammeter, it's placed in series. It all next an acid itself, think of Agatha. Agatha, placed in series, small resistance. Come on down round. Here is the resistor that we are testing for Ohm's Law. So there's your resistor. It's a fixed resistor. There's the symbol for Ohm, like a cowboy's hat. There's the voltmeter. Follow that down round. Please, blue line, follow that. See, there's the voltmeter there. Just undo that. Undo, undo. There's the voltmeter in parallel, Vince, the bandy legs. So then you come on up around, and there's your variable resistor. Look, see there, that allows it to vary. So that controls the size of this current over here. And we're back round to the cathode. And that's the circuit, and you need to know that. So we've discussed all that we need to know. So we're going to measure the current in the ammeter, we're going to measure the voltage in the voltmeter, we're going to keep the temperature of the fixed resistor constant by opening and closing the switch. We're going to vary the size of the current by using the variable resistor, and we're going to record the voltage across the fixed resistor. Now, let's have a look at the set of results that we might get. So, I'm drawing a table up here in the top left corner, and again we're talking about simple rules here. Voltage measured in volts, current measured in amperes. See the way I have the table labelled. Now here's the set of results: 0, 2, 4, 6, 8, 10. And the current was 0, 1.5 amps, 3 amps, 4.5 amps, 6 amps, and finally 7.5 amps. Fair enough? So there's the set of results that I expect you to draw a graph with. Now let's analyse what we're expecting here. Ohm's law says V is equal to I multiplied by R. So let's just talk about that. Pen let me down badly. Voltage is equal to current times resistance. Fair enough? Volts, amperes, ohms. So I'm going to slightly rearrange this, because remember, no matter what you do in this life, always keep it simple, stupid. The old KISS routine. 10. Where are you at? 10 is equal to 5 by 2. That's exactly the same as 10 is equal to 2 by 5. So I'm just going to rearrange this. V is equal to R multiplied by I. That's about face. Now I'm going to put the straight line formula in it. And the straight line formula is Y equals mx plus c. Right? And now I'm going to do a bit of mapping. So we're going to change to a different colour here. I'm going to change to red. So on my y-axis I'm going to have the voltage. Fair enough. On my x-axis I'm going to have the current. And the gradient will be R. So this is the graph that I expect to find. So I'm going to get back to a black pen. There's that. Let's do that one. That was exciting, that. And here's the other one. Now remember, there's my y-axis. So that's going to be voltage measured in volts. Here's my x-axis. That's going to be current measured in amps. Remember, there's a mark for that, and there's a mark for that. And I expect this to be a straight line graph through the origin. That's what I expect to find. That's the theory. So let's see, can we match up what we want done here? So the important thing is the gradient is the resistance. So the gradient, so I'm going to write that down. The gradient is the resistance. Right? And let's have a look at this. Go back over here again. Do you see that gradient there? Look, follow the blue spot. That gradient is constant. It's a straight line, it's constant. Yes? So let's write that down. The gradient is constant. So V is proportional to I. Voltage is directly proportional to current, right? V is proportional to I. It goes through the origin. Follow me over here again. See why it goes through the origin. So that proves Ohm's law. Now what I want you to do, come to the end of this video. Thank God. Bore myself to death. Page 456, 457. Now, I'm looking at it, and you should be looking at it now too. You can pause this, maybe never come back to it. I'm looking at the prescribed practical P6. You're supposed to know this. So I would write up the aims, I write up the apparatus, I write up the method, I then go to the table of results, and I go to my table of results, I write them in there. There's the diagram, it's the same as my diagram, right? They draw a graph. I haven't drawn a graph, but you're going to draw the graph from these results, and then you're going to give the conclusion. Fair enough? Then you're going to take good plan diagrams. I'm finding it very difficult to mark some of the work because some of the photos that you're uploading are ski whiff, and I find it hard to measure things on it. So a good plan, put the paper on a table and put the phone as parallel to the table, take a photograph of it, try to make it as big as possible. Then whenever I'm in trying to make comments on it, it's easier for me, and then you upload that to me. Again, this is time bound, and this is marked and recorded for whatever purposes it has to be used. So that's that Ohm's law done. Thanks very much. Toodle pip old bee.